Great. Hello, everyone. I'll talk to you about neurocomputational modeling of human physical scene understanding. This is work with Kevin Smith, Mario Belledonne, Jiajun, and Josh Tenenbaum. Both Kevin and Mario are first co-authors, and both contributed a huge amount of work here. Vision is more than attaching labels to objects in a scene. In addition to knowing that you are looking at apples in these images, you also see and reason about their physics as to how they support each other and what would happen if one of them is removed. And such inferences facilitate action planning and problem solving for a wide range of queries or tasks, including this particular one. Such physical inferences are essential to interacting with our environments creatively and flexibly. The focus of this talk is going to be about seeing physical properties of objects, such as their friction, rigidity, and mass, which sometimes is quite obvious. For example, here you will know them by their sizes. But other times, only with dynamic motion information, you can tell which of these otherwise identical looking objects is heavier. I'll play it once more. Similarly here, with these large cardboard boxes, you can tell which is heavier only by observing their motion, only through their motion. And obviously, all of these computations are taking place in the neural circuitry, with the recent evidence coming from both human and monkey fMRI, pointing to a network of regions in the parietal and premotor regions. That brings me to what I call the CCN challenge. And I'll use a version of the CCN logo to illustrate it for you. Cognitive science demands that the physical inferences are flexible, that it should work seamlessly across multiple tasks and new domains. Computation demands that physical inferences are fast, at the speed of online perception, that they should dynamically update with more information in the context of real life. And finally, this computation should be mappable to population level activity or neural circuitry. Our consideration is going to be very practical and should mean something like using machines composed of neuron-like units, such as artificial neural networks that are readily relatable to neural activity. Our goal is to get here, but I'll say upfront that we are not there yet. In this talk, instead, I'll tell you about a space of models that integrate these modeling goals in different ways. I'll then show you behavioral comparisons, and finally, we'll tell you about the future directions. And I should note that I'll be using this figure throughout the talk to keep track of our progress. I come to this challenge from the perspective of cognitive science, and in the recent years, our lab developed a computational framework to explain the flexibility of human physical reasoning. In this framework, the targets of perception, be it vision, audition, or touch, is what we refer to as physical object representations. In engineering terms, we characterize them using the way objects are represented in physics engines and graphics engines, a minimal description of shape, material, and dynamical properties needed to simulate natural-looking scenes over short time scales. These are embedded in probabilistic models to unambiguously and rigorously specify domains and tasks, and are integrated with modern neural networks to solve the otherwise computationally costly inference tasks. Okay, let's take this framework and put it to use in the scenario of this talk. This scenario basically looks like this, with an object on a ramp and another on the ground at the table. The conditional independent structure, or the state space model underlying this scene, consists of a world state evolving with a physics engine and observations generated through a graphics engine. The latent variables in this generative model, the physical object representations, consist of substance, geometry, and kinematic properties of objects. If we take them and plug them into our generative model, this is what it looks like. And below, I am showing 4 videos randomly drawn from this generative model, each showing an initial and a final frame. It is showing some of the variability in the generative process. So this is the generative model. But physical inference is the inverse of this operation and can be characterized using Bayes' rule. Once this inference is accomplished, which often is very difficult, as alluded by Ryan Adams, you will get something very cool. It will support broad generalization. What if the ramp is more or less inclined? What if there is a threshold on the ramp? What if the table is bumped, etc.? The traditional approach to solving this problem is a flavor of the analysis by synthesis approach, where given an observation like this, let me play it again, the model randomly guesses initial configuration until forward simulations matches the input. Here is an example run of this algorithm. You will see it tries out different initial configuration until it better fits the observed velocity profile. Note, though, that this algorithm does something really odd. It starts from a random guess without looking at the input first. And inference is pretty slow and iterative, as shown in this plot with the number of iterations on the x-axis and the quality of the current best guess on the y-axis. And I'll add one final layer to this slide to say that we refer to this model as the ideal observer model, in that it uses the true underlying generative process and computationally is not constrained. We let it run until convergence. You can extend this algorithm to make it use visual inputs in a more bottom-up fashion. It is a data-driven MC Monte Carlo Markov chain algorithm using a connet like this to initialize inference in the iterative algorithm. Although, as shown here in these red curves, it helps that it starts with better predictions and converges faster, it is still highly iterative and computes a single percept per video as opposed to dynamically updating its beliefs. In terms of our modeling goals, both of these approaches are in this corner. Although the data-driven ideal observer model is a bit more efficient, a bit more neurally plausible, in that it uses a connet that models aspects of the ventral stream processing. In modeling behavior, we will only work with this ideal observer model, as both of these models compute a single percept per video and have similar convergence behavior. So we wish to take this ideal observer model and arrive at an algorithm that is both fast and dynamically updating. We will accomplish this in two different ways. First of this is a particle filter algorithm that uses very few particles to represent beliefs per time step. It involves dynamic belief updating of physical object properties as more motion is observed. In our implementations, we found that this algorithm is an order of magnitude more efficient or faster than the ideal observer model. Second is to build a recognition network. Let me tell you more about it. The core technical idea here, in a brief slogan-like form, is that Judea Pearl meets Jeff Hinton. And this is very related to some of the things from Ryan's talk. What it means is that we build a recognition model, in this case an artificial neural network, based on the overall conditional independence structure in the generative model. And to contrast to the earlier work, instead of using graphical models, we use specialized probabilistic programs that are also known as probabilistic simulation engines, which provide richer and more expressive model families. Before I go on to say how we do it exactly, let me give a justification for pursuing this avenue. We found that such recognition model building approach is useful both in neuroscience to explain multiple stages of processing in the monkey ventral visual cortex, and in engineering in computer vision to build some of the most accurate 3D perception systems. So I remind you that this is our generative model, and physical inference is this inverse operation. Here with this model, our goal is to obtain good estimates of the latent variables. It is a kind of amortized inference. And we will do so by training a recognition model using hallucinations or dreams from the generative process. So at each time step of the recognition model, input is a frame from the video, targets are the latent variables. This inference gets integrated over time. In a moment, I will tell you about the details of what happens at each step of this model. But before, note that there is a part of this as part of building this recognition network, we had to introduce these auxiliary variables that weren't part of the generative model. They are what we call the binding parameters, or simply attention, and they keep track of which object state to update at each time step and where in the image to attend for its evidence. So let's look at what happens at each time step of this recognition network. First, input frame and image is encoded using a pre-trained convolutional neural network and attention. Second, we encode the state of the world, including the states of individual objects and their relations, using a graph network. Third, these are fed into a recurrent neural network, an LSTM. This LSTM is not really for learning physics, but for providing a temporal embedding space to enable inferences about the latent physical properties of objects, such as mass and friction. And finally, latent variables and the binding parameters are decoded from the hidden state of this LSTM. Excuse me. We trained this network using 1,000 random draws or hallucinations from the generative model. And there are two objective functions for training. One, a supervised loss for training the network to map sequences of images to their underlying latent variables, and an unsupervised loss for learning the binding parameters. Here is an example showing the temporal dynamics of the model at the time of inference. At the top is an input video here showing its initial, final, and collision frames. Each panel below is showing a latent variable. Only 3 are shown here for illustration. X-axis shows time, or the number of frames, and y-axis shows value of the latent variable. You can see the model captures the ground truth and tracks it around the time for all of the latent variables quite accurately. So with respect to our modeling goals, the particle filter algorithm takes the ideal observer model and makes it dynamically updating and computationally efficient by applying resource constraints, by using very few particles. And this model compiles, the recognition network, compiles the kind of inference the particle filter algorithm does into a neural network. Note that this model doesn't use the generative model at test time, but it is mappable in the sense we defined earlier. It is composed of basic ConvNet and recurrent neural network layers that constitute readily testable hypotheses about population-level activity. Okay, with the 3 of these models, we are now ready to look at the human behavior. The task, the behavioral task, was to judge the relative mass of the ramp and the ground objects. A trial in the experiment looked something like this. Subjects saw the video at the top that played for only 1 time before going dark. Then they had to enter their judgment, their response, using the slider bar at the bottom, with one hand saying ground object much heavier and the other hand saying the ramp object much heavier. Okay, now to be able to study dynamic belief updating, we manipulate 1, amount of the video scene, and 2, congruency of the substance versus texture of an object. First, we varied the amount of the video scene at these 4 different levels. Let me play that. Let me play it a couple more times. However, just varying amount seen is not enough to study dynamic belief updating. Given an initial state, including the substance and size of an object, one can readily form a reasonable guess of their relative mass without needing to see any motion at all, really. However, what we do here is, in some critical trials, we manipulate the weight of an object, weight of the ramp object, so that it is either heavier or lighter than usual without changing its appearance. If we take this wood puck and make it heavier than usual, then the end state will look like something like this, which is quite different from the congruent end state. Combining this incongruence manipulation with the amount seen, now we can study belief updating behavior in humans. But before I show you that, let me say that the subjects were able to perform this task. On normal trials, their judgments were reasonably correlated with the ground truth. So how do subjects update their beliefs? In this plot, x-axis is the amount seen with its 4 levels, and y-axis is the relative mass judgment averaged across subjects. We expect that as they see more of the video, their judgments should be relatively constant for the congruent trials and increase or decrease, in this case increase, with incongruent trials. Here is the data for this particular trial, and by and large, it fits those expectations. How does that behavior compare to models? Here you are seeing the results of the recognition network at the bottom, with dashed lines showing models' predictions overlaid on the data. Both this and the particle filter algorithm mesh the data quite well, even though here the ideal observer model is not too far from the data. It has this particular property where it flattens out as soon as there is any information revealing the collision event. Here is the data and model comparisons we just saw. Here is two more examples. Again, both approximate methods, the recognition network and the particle filter, matches the data quite well. Whereas with the ideal observer model, we consistently see that it flattens out like before. If we pull together all trials, including normal and incongruent trials, we find that both the recognition network and the particle filter algorithm match the data pretty well. But as you can see under this metric, ideal observer model is not too far off neither, mostly because of the fact that humans are fairly accurate in the congruent trials, which is the majority of the data you are seeing on this plot. Yet, you also see several patterns emerge in this scatter plot that seems suspicious. Indeed, when we fit models to normal trials, we find that they all fit the data fine. But when we test how well these fitted models generalize to explain behavior in the incongruent trials, then the difference is quite clear, with the recognition network and the particle filter accounting for the data much better than the ideal observer model. Okay, in summary, I told you about the ideal observer model, particle filter model, and the recognition network, all building on this computational framework of physical object representations. And the behavioral results provide evidence for the integration of causal generative models and online data-driven inference mechanisms as accounts of how people make judgments about dynamic physical properties. And that brings me to my future work. First, we are starting collaborations within the Center for Brains, Minds, and Machines at MIT and other places to test versions of these models using high temporal resolution recordings. But we believe that there is a lot to be done here, so experimental folks, if the task or the models sound interesting, please get in touch with us. And second, RAM scenario is nice, but constrained in several important ways. So we are extending this to more complex scenarios with varying number of objects, occluding scene elements, richer dynamics, and multiple tasks. For instance, here you are seeing two identically configured towers, and we ask subjects to determine which oddly colored block is heavier by just watching them move like this. Finally, let me end on by going back to our modeling goals once again. I showed you a number of models, but there really is a landscape of models with multiple routes to integrating all three of our modeling goals. To mention just one here before finishing, we are considering emulating physics engines and graphics engines with more neuron-like machines. Promising directions here include what is called neural physics engines, or by using other neuron-like machines such as tangled program graphs. Okay, that's it. Thanks.